The reason we were interested in focusing on injecting fairness into a machine learning model is this experience that I had at the end of my PhD, where we saw that many of these different models have biases. The problem with thinking about bias in machine learning models in a healthcare setting, but then also in other settings as well, where we acquire data from a natural environment, is that usually you can't really fix the underlying data bias. We just have some groups that we're going to sample less from, potentially because there are fewer people from that population. There's always going to be minority populations in any data set. And so we don't want to be in a situation where we say, just because this kind of data has a minority population, we know we're not going to work as well on that kind of data. And so there's a really popular kind of learning that we do for images called deep metric learning. And what it is it takes a bunch of different kinds of images and says, I don't really know what sort of underlying representation I should have to say that these two images are similar. I probably don't want to just look pixel by pixel and subtract them. Let's make a deep neural network learn a representation in which two pictures of dogs embed to a very similar space and two pictures of cats embed to another space that's also very similar. And so this kind of learning, this metric learning, is really cool for images because it means that we can understand how any two images might relate to one another, so that at retrieval time, if I see a brand new image I've never seen before, I can immediately see where other images like it would have been mapped and then give it a label that makes sense, like dog or cat. So the problem is, if you use standard deep metric learning techniques that are still state of the art, if you have a minority class, we don't have many labradoodles in a data set. That part of the embedding space doesn't get learned very well. And so what that means in a very human setting is if you have significantly fewer examples of black faces than white faces, we're going to learn a less rich representation of black faces. And so we'll have a embedding space that embeds most black faces to the exact same place, even though they're not the same person, just because there's so few examples of black faces. We didn't want to have that happen in general, and if you just train a vanilla model that's trying to do retrieval, it will, by default. And so we're trying to decorrelate these attributes and give some independence so that you're learning a representation that forces richness for different kinds of people. And that's really important in these kinds of applications, because often we think, just throw data at the problem and learn whatever you can learn. But here in the Parade paper, the goal is to say, we know something extra about this data. We know that, for example, there are fewer examples of dark skin. And we want to make sure that that's input we give to the model so that it can learn partially to decorrelate the attribute and then have a richer representation. And that means that when we try to retrieve a new face or classify an unseen face, we'll have a better performance for minority groups.